स्ट्रक्चर। तो ये स्टैटिक डेटा स्ट्रक्चर, नॉन स्टैटिक डेटा स्ट्रक्चर, लीनियर डेटा स्ट्रक्चर, नॉन लीनियर डेटा स्ट्रक्चर, ये सारे इंटरव्यू में पूछे गए क्वेश्चंस हैं। लीनियर डेटा स्ट्रक्चर मतलब क्या? अ डेटा स्ट्रक्चर इन विच द स्टार्टिंग एंड एंडिंग पॉइंट्स आर फिक्स्ड, जहां मुझे पता है कि बॉस यहां से मेरा डेटा स्टोर होना शुरू हुआ है और यहां तक मेरा डेटा स्टोर हो रहा है। So such type of data structure is called a linear data structure. यहाँ पर हम जिस लैंग्वेज को यूज करेंगे फॉर इंप्लीमेंटेशन ऑफ अ डेटा स्ट्रक्चर, दैट इज अ सी लैंग्वेज। हम पूरे डेटा स्ट्रक्चर के कॉन्सेप्ट को इंप्लीमेंट करेंगे सी को यूज करके। हेलो दोस्तों, स्वागत है एक बार फिर आपका डेटा फ्लेयर डेटा स्ट्रक्चर के इस फ्री कोर्स में, विच इज वन ऑफ द मोस्ट डिमांडिंग, मोस्ट अवेटेड सब्जेक्ट। ओके, तो बात करेंगे आज हम लोग डेटा स्ट्रक्चर के बारे में, ठीक। लेकिन जब भी हम कोई नई टेक्नोलॉजी या कोई भी नया कॉन्सेप्ट शुरू करते हैं तो सबसे मोस्ट इंपॉर्टेंट कॉन्सेप्ट जो है वो ये है व्हाई डेटा स्ट्रक्चर। ओके, कि डेटा स्ट्रक्चर हमें क्यों पढ़ना है, व्हाई देयर इज अ नीड ऑफ डेटा स्ट्रक्चर। ओके, सो वंस वी कंप्लीट दिस कॉन्सेप्ट तब हम बात करेंगे व्हाट इज डेटा स्ट्रक्चर, कि डेटा स्ट्रक्चर क्या है। क्योंकि कई बार बच्चों को कंफ्यूजन होता है, जैसे डेटा स्ट्रक्चर कोई लैंग्वेज है, डेटा स्ट्रक्चर कोई हार्डवेयर है, डेटा स्ट्रक्चर कोई सॉफ्टवेयर है। सो एग्जैक्टली डेटा स्ट्रक्चर है क्या? ओके, तो सबसे पहले हम बात करेंगे व्हाई डेटा स्ट्रक्चर के बारे में, कि डेटा स्ट्रक्चर, व्हाई दिस सब्जेक्ट इज सो मच डिमांडिंग। बात जब हम करते, हाउ मेनी वेज वी कैन स्टोर द डेटा इन मेमोरी, कितने तरीके से हम एक डेटा को मेमोरी में सेव कर सकते हैं फॉर एफिशिएंट मैनर, ठीक है। दैट शोज द स्ट्रक्चर ऑफ दिस डेटा इनसाइड द मेमोरी। तो ये पूरा पेपर हमें क्या बताएगा कि बहुत से डेटा को मेमोरी में हम कितने तरीके से सेव कर सकते हैं, सो दैट व्हेन वी रिट्राइव द डेटा, कि जब भी हमें उस डेटा की रिक्वायरमेंट होगी, सो ये डेटा हमें मिनिमम टाइम कॉम्प्लेक्सिटी के साथ मिले। जब इस डेटा को मेमोरी में सेव करेंगे तो हम ये चाहते हैं कि स्पेस कॉम्प्लेक्सिटी रिड्यूस हो। तो इस पूरे पेपर में हमें केवल एक बात करना है कि बॉस, हाउ द डेटा इज टू बी स्टोर्ड इनसाइड द मेमोरी। एक डेटा को मेमोरी में कितने तरीके से हम सेव कर सकते हैं, व्हाट इज द स्ट्रक्चर ऑफ दिस डेटा, कि जब एक डेटा मेमोरी में सेव होगा तो उस डेटा का मेमोरी में स्ट्रक्चर क्या होगा। देयर आर डिफरेंट फेज ऑफ डेटा स्ट्रक्चर, जहां पर हम अभी बात करने वाले हैं, ठीक। डिटेल में देखते हैं कि डेटा को मेमोरी में हम स्टैक फॉर्म में सेव कर सकते हैं, डेटा को मेमोरी में हम लिंक लिस्ट फॉर्म में सेव कर सकते हैं, डेटा को मेमोरी में हम अरे फॉर्म में सेव कर सकते हैं, वेरिएबल के फॉर्म में सेव कर सकते हैं। तो व्हाट इज द डिफरेंस बिटवीन ऑल दिस थिंग, कि जब एक डेटा को हम मेमोरी में सेव करेंगे तो डिफरेंट तरीके हैं हमारे पास, लेकिन जब उन कॉन्सेप्ट को हम इंप्लीमेंट करेंगे तो उनमें क्या डिफरेंसेस है, ये बात करेंगे हम डेटा स्ट्रक्चर में। सो एग्जैक्टली दिस पेपर इज ऑल अबाउट द स्ट्रक्चर ऑफ अ डेटा इन अ मेमोरी, कि जब भी एक डेटा मेमोरी में स्टोर होगा तो उस डेटा का मेमोरी में स्ट्रक्चर कैसा होगा, कितने तरीके से हम एक डेटा को मेमोरी।
Hi guys, my name is Nitish and you're welcome to a very
Welcome to this course on mastering technical interviews for software engineering roles. These interviews often hinge on your ability to confidently solve problems using data structures and algorithms, which can feel challenging without the right foundation. In this comprehensive course, Parth from Destination Fang will strip away the intimidation and equip you with the essential knowledge, starting with the core concepts of data structure, algorithm, and fundamental analysis like time and space complexity. You'll learn how to judge an algorithm's efficiency using Big O notation and apply this important skill to code blocks. The course covers almost every major data structure and algorithm pattern, from arrays, linked lists, stacks, and queues to advanced topics like trees, graphs, dynamic programming, and backtracking. So, good luck learning.
Hello friends, hope you are having a fantastic day today. This is going to be 50-hour long course that contains everything there is to know about technical interviews, data structures and algorithms. There are about 20 concepts that I have created that comprise the entirety of technical interviews, and that contains different data structures, different algorithms and different coding patterns. We are going to cover each and every one in very much detail. We will understand the concept for them, and then we would solve lots and lots of interview problems associated with that. By the end of this course, you would have solved close to 200 most asked, most liked and most popular interview problems, and you would be able to solve majority of technical interview problems out there. And then it's just a matter of sheer practice that you will have to do on your part. I can guarantee you that this is going to be a very high quality in-depth course where it is completely beginner friendly, and we will go deeper and deeper into the most advanced topics, and I will try to explain it in as much detail as I can, so you can be absolutely prepared for anything to come in your technical interviews. Now, a quick introduction about myself. My name is Parth Vyas, and I have bachelor's and master's in computer science. I have been in the IT industry for close to 10 years now, and I have worked at companies like Microsoft, RBC, Nokia, and currently working as a solutions architect for Cineplex. I have joined my career as a junior developer and have gone through multiple transitions. I have been absolutely blessed by a lot of important mentors who have guided me correctly in my career, and this is something me giving back to the community. Now, I also run my own YouTube channel named Destination Fang, and I would highly encourage you if you can go and support me on that channel as well. I teach about how you can go ahead in your career.
ओके सो यू वांट कि मैं अपनी स्क्रीन भी दिखाऊं तो श्योर तुम भी पढ़ लो one second. Okay, this will be fine. Oh, oh wait. Yeah. Now, okay. देख पा रहे हो स्क्रीन? अबे देख पा रहे हो, सब दिख रहा है तुम्हें? इसको इधर कर दो, बस साइज छोटा कर देता हूँ. और भाई इससे कॉपीराइट ना आ जाए मेरे को. यहाँ पे मैं अपनी तरफ से जस्ट टू बी सेफ ये स्क्रीन पर रहेगा ताकि कोई कॉपीराइट ना आए, समझ रहे हो? Let's get back.
And how you can ace your technical interviews, behavioral interviews, and system design interviews. And your support matters a lot for me, so it can motivate me to keep making more videos like this. On top of it, you can stay up to date on the latest and greatest things that I'm currently working on.
Yeah,
Few
that's
fun
right.
facts about me: I love going on hikes, I love watching movies, and I love playing with my twin daughters. I am based in Canada, and this is a beautiful country. So if you get a chance to visit, please come and see it anytime. Now, I would not deviate from the main topic, that why we are here. So without any delay, let's get started. Now, what is DSA? DSA stands for data structure and algorithm. Now, everything in computers is made out of data. These are the bits and pieces of zeros and ones that hold all the information. It can be a text or a book or a PDF or the video you are watching. Anything can be represented as data, and the way we store and organize the data is referred to as data structures. Now, there are many different ways of storing data. You can store them in a straight, fixed, given format that can be defined as array. You can have one bit of data live over here, next live over here, and after one, the next lives over here. But this guy does not know where this guy exists, and that's an example of linked list. And there are bunch of other different ways to understanding different data structures. Now there are linear data structures, non-linear data structure, hierarchical data structures, hash-based data structures, and they all have different purposes, which we will learn more in the classification of data structures. Now let's understand that what is algorithm. Algorithm is nothing but following step by step to complete certain procedure and achieve an expected outcome. Now this can be anything.
आपका कुलचा
इस चीज का मैं कुछ नहीं कर सकता.
अब क्या है कुलचा
वाह क्या बात है, क्या बात है.
If we strictly talk about from the perspective of computer science, there are algorithms that do certain things really well, like sorting items, searching any particular item in the existing given data structure, recursion, dynamic programming, greedy approach, divide and conquer. And these are all the strategies that we typically use in our day-to-day operations as well. We just don't realize that these are algorithms. And then there is the combination of data structure algorithms that help us solve many complicated problems. So that's why the companies that are substantially large in the IT industry, these are the FANG companies or top tier IT companies, they usually build products that scale up to millions and billions of users. And they want to have the most efficient, most optimal approach to any given problem. And that's why they love asking these questions to understand the technical prowess and proficiency of any candidate. And that's where you need to be learning about these things. Now, how does a solution can be defined as optimal? Well, there are two things that defines that, and that is called space complexity and time complexity, and they are usually referred by big O notation. Now, we will understand the full theory on that in one of the sections. But how does companies typically evaluate your solution? They are looking for number one, whether you can reach to the optimal solution or not. That's a basic criteria. But that is not just the only criteria. Now, in a typical interview process, you are expected to go through somewhere between 3 to 5 rounds of technical interviews, each lasting about 45 minutes to 1 hour. And for each of the interview, you are expected to solve anywhere between 2 to 3 medium to hard DSA problems. Now, you are being judged based on your thinking abilities, your communication, whether you are a good person to work with. Can you think of different scenarios, different edge cases? Are you able to come up with the optimal solution? What does your approach looks like? If you have a suboptimal solution, can you reach to that optimal solution? Can you ask for proper hints? Can you convince your recruiter or interviewer about your solution? Can you walk through it? Can you code it out? And you know, the complicated part is they typically don't give you a full IDE or editor. They typically ask you to solve this problem on a whiteboard if it's in person, or on a Google Doc if that's going to be a virtual interview. So that's why there are a combination of skills that you will have to accumulate throughout this course and your preparation journey to be able to clear multiple different technical interviews. And we will learn that in the next section. Now, how do we even judge an algorithm? Well, there are three things that we are looking for. First one is the accuracy of algorithm. That is quite straightforward, that if I expect my algorithm to generate pizza or find the shortest number out of all of these given numbers, if it is exactly doing that, which means my algorithm is accurate, and it needs to do that for all the different edge cases and all the different scenarios. Second thing is time complexity, and third thing is space complexity. So first, let's understand that what is time complexity through an example by these deck of cards. Time complexity is nothing but how much longer will it take for you to complete your algorithm or your task if the number of inputs keeps on growing larger and larger and larger. Let's try to understand that currently I have these deck of cards and they are currently just randomized. If I lay them flat on a table, and let's say that for simplicity I'm trying to figure out that where does heart of 6 lies amongst these cards. Now I don't know, but I can keep on opening all the different cards randomly until eventually I found out to a card that is heart of 6. And notice that I found heart of 6 right here. But how many cards did it took me to find this value? It's just like finding a needle in a haystack. You need to go one by one. And if I had like million cards and all different unique entries, it might take me like million attempts before I reach to the card that I'm particularly looking forward. So in this case, we can notice that the time it takes for me to complete the expected task increases linearly with the increase in the number of inputs. So we can call this time complexity of big O of n. Now, big O is the definition or a way we write the time complexity and space complexity, and we are going to talk all about that in a separate topic. But now let's just say focus towards this. Now let's see that how does time complexity change based off of how we have our data being scattered or how we change our algorithm. Let's take an example. Now in this case, we are going to sort all of these cards in ascending order, and then we are going to lay them flat once again on our card. So this is going to be the smallest value, and then we are going to keep on adding all of these values on this table. Now notice that in this scenario, once again we are trying to find that where does heart of 7 is present in this deck of cards. Now I don't know, I can't see them, but I know for a fact that this one is the smallest value, this one is the largest value. And if heart of 7 is present, let me just open the middle value. So middle value is heart of 6. So I know for a fact that all of these cards are definitely going to be smaller than 6 because it's already sorted. So I don't even need to look at these cards. I can ignore all these 4 cards, and then I only worry about these 3 cards. Once again, I'm going to open the middle card, and this one is heart of 8. Now I know because this is sorted, so these two values are always going to be greater than heart of 7. So this card has to be heart of 7, the lucky card. And that is what we currently have on our table. Now notice that once again we had again 8 or 9 cards, but we only needed to open 3 cards in order to find the card that we were looking for. This one is an example of logarithmic n time complexity. Why it's logarithmic n? Because with every single task or every single step we make, we are essentially eliminating 50% of all the inputs in one go. So here we eliminated 4 cards, then from the remaining 3 we eliminated 2 more cards. If we had million cards in just one opening of a card, we would have eliminated 500,000 cards. In the second opening, we would have eliminated remaining 250,000 cards. So even if we have like 10 million cards, we can very quickly find the value that we are looking for, and that is an example of big O of log n time complexity. Now let's talk about some other time complexities and other examples. Now, the most basic time complexity is a constant time complexity. Constant time complexity means that if it takes us, let's say, 1 second to do a one job for 10 inputs, it will once again take us like 1 second, even if we had 100,000 inputs. What's an example of that? Let's presume that we currently have this ice tray where we have bunch of different black chickpea beans associated with that. And they are currently placed in a sorted array, in a sorted bucket, and for each number it corresponds to total number of chickpeas being present. So like this one is first one, so it only has one chickpea. This one is second one, it has two chickpeas. Now in this case, if I have to figure out that show me 5 chickpeas, let's say that that is what I want from my algorithm, I can very quickly say that this fifth number is going to contain 5 chickpeas. So I can quickly take them out and then start counting that there are going to be 5 chickpeas in my hand. Now, even if I had million of these, and presumably I have like hands longer that can reach up to all of these million associates, I can very quickly find any number of chickpeas I want from this given example. So this would be a scenario where the time complexity is going to remain constant. Next one is logarithmic time complexity that we already saw an example using the sorted cards. And next, we also saw an example of big O of n time complexity, where the time increases linearly with the given input size. Now let's talk about big O of n square time complexity. Now for this n square time complexity, let's presume that we currently have these two decks present. What we are going to do is we are going to find a card from this deck, and this corresponds to, let's say, number 8. Now we are going to keep on scanning this deck until we find number 8. So we found number 8. That's great. Once again, we are going to repeat the same process, and this is going to be 3. So this one is 3. Once again, we found the match. Now this one is a joker, so let's just ignore that. This one is 7. So now for the 7, we will try to keep on shuffling through the deck until we find the appropriate 7, and in this case it took us slightly longer, but we eventually find it. It's basically a matching between two separate decks. Now notice what is going to happen. For every single card that is currently present in this deck, worst case scenario, it could be possible that we might have to scan this entire deck before we can reach to that end conclusion. So for each of these n values, we will have to do n work. It's loop within a loop in order to find the established goal. And that is an example of big O of n square time complexity. Now for n cube time complexity, basically we are just going to have 3 set of decks where we will take value from one deck, then we will try to find a matching pair from the second deck. Maybe it could take us as long as it takes, and then we will try to find another matching from the third deck. So this can take substantially longer, but overall this is what n cube time complexity means. It's once again loop within a loop within a loop. Now let's talk about some really large time complexities. So first one comes to mind is 2 to the power n time complexity. 2 to the power n complexity means that if you have an input that increases, the time it takes for you to generate the output multiplies by 2 every single time. And what is an example of that? Let's say that we currently have a coin. Now this particular coin only has two possibilities. If I flip it, it can either be heads or it can be tails. That's it. But the thing is, what if I add one more coin into the mix? Now the number of possibility are multiplied by 2 again, because we can have two heads, we can have one head and one tail, we can have one head and another tail, or we could have two tails. So in this case, we have four possibilities. If we add one more coin, the possibility once again multiplies by 2. We could have eight possibilities. If we have one more coin, it once again multiplies by 2. We could have 16 combinations of heads and tails. If I add one more coin, the possibility multiplies by 2 again. So we could have 32 combinations. So notice that when we started merely with just two possibilities of flipping a coin, it has very quickly grown to 32 possibilities just with the addition of 4 input values. If I keep on adding the input values like 10, it's going to be 1024, and so on and so forth. So it's going to become very large very quickly, and these are the time complexities that we are typically trying to avoid, or it becomes very tricky to work with them. So do you think that this would be the worst time complexity? Well, you might be mistaken. There is also some more time complexities that are more complex than this, and that could be in the factorial time. So what does factorial time? Let's try to understand it with a simple example. Let's say that we currently have these three cards. Treat it as like three seats in a bus or an aeroplane or a movie theater. And then we have three friends who are currently trying to have a seat on these three different places. What are the different combinations we can have them seat in these places? Well, in the first seat, potentially all three can sit. That's very fair. Now, amongst all three can sit, if one sits, then for the second seat, the number of possibilities are 2. And for the third seat, the number of possibility is 1. So if we have to quantify that, what are all the different permutations and combinations? There are 3 possibilities that can have a seat on the first position. There are 2 possibilities on the second position, and there is 1 possibility on the last position, and it's a multiplication of them because it's permutations and combinations of all the different people trying to have a seat on the first, on the second, and on the third. So it's going to be 3 multiplied by 2 multiplied by 1. So in total, we can have 6 possibilities. If I add one more card into the mix, and if I add one more person, now the whole dynamics change, because on the first position, potentially all 4 people can sit. On the second position, potentially 3 remaining people can sit, 2 and then 1. If we do the multiplication, it comes up to 24. If I have one more card And once again, if I am trying to have one more person have a seat over here, now it becomes even more complicated, because on the first position, any of these five people can sit. So it's five possibilities, then four, then three, then two, and then one. So it's a multiplication of all of these. And this comes up to 120. If I add sixth value, it's 720. So notice that how quickly the number grew from just having six for the three time complexity to having 120 possibilities for the remaining two. So this is how exponentially the time complexity grows for a problem that involves factorial time complexities. Now, there are some real cases where we actually do deal in factorial time cases, and we try to improve upon them using dynamic programming, and we are going to see a lot of examples of that. Now, let's try to understand that why do we use the terminology big O to define time complexity or space complexity. Whenever we are defining the speed of an algorithm, we would say that it runs in order of the growth rate based off of given input size. What I'm trying to say is that if my current input is 10, it runs in, let's say, 10 seconds. And if my given input turns to 1000, it runs into 1000.